All right, so welcome back to your class. The plan for today is to continue with the standard normal distribution, finish up our discussion of that, and then move on to general normal distributions. Uh, so the normal distribution is a family of distributions parameterized by mu and sigma, and that's what we're going to be working towards today. The quote of the day today is by financial guru, late financial guru, I suppose. He passed away maybe about a year ago. Charlie Munger, one of the kind of two, I don't know what you'd call them, like legendary heads of Berkshire Hathaway. And I figure I will just play you an excerpt of this, of this, sorry. I'll play you an excerpt of this video on YouTube. This is a great speech of his. I really enjoy it. It's not just about finance and economics, but about a lot of how psychology impacts how we make decisions. And so the title is The Psychology of Human Misjudgment by Charlie Munger, full speech. Let me actually pause the recording. How do I do that? All right. All right. So basically what Charlie's point is Berkshire Hathaway, the company has been successful and profitable year after year for many, many years in a row, kind of far outside of what models like the efficient market hypothesis would suggest. And, you know, this economist won a share of a Nobel Prize for his work on the efficient market hypothesis. And when people would say, well, if you look at Berkshire Hathaway, they're, they exist, they're performing this way, that your theory says it's impossible for this to happen, or maybe I shouldn't say impossible, but extraordinarily unlikely. How do you explain that? And at first he explained it as a 2 sigma event. Okay, well, there's a bunch of companies out there, just by chance, 1 in 20 or so are going to be more than the 2 standard deviations away from the mean. That's pretty reasonable. And then Berkshire kept performing outside of expectations year after year. And then it was a 3 sigma event. There's, thousands of companies out there. Of course, a few of them are going to, be more than 3 standard deviations away from the mean. And then like Charlie says, I don't know if Charlie's blowing this a little bit out of proportion, but he says he got all the way up to 6 sigmas, that it's a 6 sigma event. Well, once you're at 4 sigmas, you're at something like 1 in 30,000. When you're at the 6 sigmas, it's like, okay, well, at this point, you're just making stuff up, right? So instead of saying, okay, our model doesn't capture everything about the real world, everything about this economic idea of the efficient market, it's a good model, it's useful, but it's not completely correct, and there are exceptions to it. When you kind of have a Nobel Prize, you have to dig in your heels a little bit and not make so many caveats. So we have a tendency to ignore new information, or maybe take that new information and really twist it in a funny way to make it seem like it fits what we were saying all along, when really it refutes what we're saying. So that's why I like this statement from Charlie: better to add a sigma than change a theory, because we're laughing about this Nobel laureate economist doing it, but this is kind of what we do every day. And this is what most people do most of the time, is we have a certain worldview, we have contradictory information that comes in, and we just either ignore it, or we kind of twist it to fit into our theory of how the world works, instead of changing our theory of how the world works. And there's validity to that, right? If we were always just being buffeted around by new information, that's not a great way to go about life. But it's good to recognize that there is that bias, that confirmation bias. Okay. So really quickly, recall the normal distribution. It's symmetric, peaked in the middle, tails off to both sides. Here's a little funny little meme of the normal distribution, meme or joke or whatever it is. The normal distribution and the paranormal distribution in honor of Halloween. And recall that we have symmetry about the mean, which we can use to help us answer some probability questions. We can use the complementary event rule. This is defined for all real numbers, x, and Recall the probabilities are represented by areas. Okay, so let's pick up where we left off last time and look at an event like this, probability that z is between negative 0.35 and positive 1.24. Zoom in just a little more here. There we go. And again, what did we do? Well, the first thing we do is we draw a picture of the event we're interested in. Let me put -1 on here as well at this other inflection point where we go from curving up to curving down. So negative 0.35 is maybe around here. And positive 1.24, maybe about there. Okay, so what do I know about this area? I don't think, really confidently say whether it's bigger than or less than 50%. But remember from last time, we did the probability that the z is between -1 and 1 was 68%. So we said that if I have my normal distribution, my standard normal, here's 1, -1, here's 2, -2, 3, and -3. Between -1 and 1, that was about 68% area. And the symmetry means we have about 34% between 0 and 1 and 34% between 0 and -1. We've got 95% that are within 2 standard deviations of the mean. This was an exercise I left to you to show. So this entire area between -2 and +2 is 95%, but we've already got 68% accounted for. So that leaves us with what? Something like 26, 27% between these two areas, or maybe something in the ballpark of 13% in each of these. And then not too much outside of here. Outside of -2 to +2 is only about 5 percentage points. So about, 2 percentage points, 2.5 percentage points to the left, and about 2.5 percentage points to the right. Hopefully this roughly adds up to 100%. So what do we have? 26 plus 68. Having very much a brain fart moment. Yeah, that I was off by 10. I just added wrong in my head. So yeah, that looks good. So I noticed that my area covers, or my event covers all of the area from 0 to 1, a bit of the area to the right of 1, and a bit of the area between -1 and 0. So it is going to include all of the 34%, a bit of this 34%, and a bit of this 13%. I think an answer in the ballpark of 50% is about what I'm looking for. If it's 40% or 60%, I'd probably be fine with that. If it was 90% or 10%, I'd be very suspicious. So I can get an idea of the size of the answer I'm looking for. So this was a more challenging event to estimate, but I think it is good to estimate for two different reasons. One, it helps us to just kind of understand normal distributions a little better when we do this estimation. Gives us a little bit better of like a gut feeling of what's going on. And sorry, I was messing with my PDF and lost my train of thought, but I think it's good to estimate because it gives us a little bit of practice there, and it gives us something to check at the end. Now, our issue that we are running into is that our table gives us areas to the left, but here we have an area between two numbers. We would like to rewrite this area as a sum or difference of areas to the left. And in this case, I can look at the area to the left of 1.24. That includes all the area that I want. namely the area between negative 0.35 and 1.24. But it also includes a bunch of area in this left tail that I don't want. So I just get rid of the area in the left tail. I do minus that left tail area to the left of negative 0.35. So I can construct the area between the two numbers by taking the area to the left of the rightmost number and then subtracting off the area to the left of the leftmost number. These are both left tail areas, so I can look them both up on my table. Or, and I guess I'll leave it in blue. Or in other words, the probability then z is between negative 0.35 and 1.24 is the probability z is less than 1.24 minus the probability that z is less than negative 0.35. Again, I strongly recommend drawing the pictures because especially for this last probability here, it's really easy to look at our initial event and get that last probability wrong and mistakenly make that probability z bigger than negative 0.35. But we're getting rid of this area. So this is the area related to negative 0.35 that's not in the event. That's why this inequality sign points the other way. And these are numbers we can just look up off our table. So let's jump over to our table. And here I want probability z less than 1.24. I want this picture with the bigger area. I see that's associated with the positive z-score side because 1.24 is positive, and my picture looks like it matches the picture that I've drawn over here. And I'm looking for 1.24, so I go to my index row related to 1.2, accurate to the tenths place. And then I go to my 0.04, my 400ths place column. And I look here and I get 0.8925. Okay. So that's the area to the left of 1.24 on a standard normal distribution. Then I subtract off the area to the left of negative 0.35. That is a negative z-score. We're going to be up here. I see that this picture matches my second picture on the right over here. So the pictures match, the algebra matches, negative z-score. So probability z less than negative 0.35. I'm going to come all the way down to the bottom here for the negative 0.3 row. And then the 0.05 column, if I kind of trace it down, it ends up being this column. Remember, our columns start at 0 hundredths. So we're at like negative 0.30, negative 0.31, 2, 3, 4, and here is negative 0.35. So that's about 0.3632. Then I jump over to my calculator. I did finally figure out the problem with my calculator. It was actually starting up just fine, but when it would maximize so that I could see it, it was like way off the screen on the desktop. And so I don't know why it's doing that, but if I go in and like click and I can tell the computer to maximize it or fit it to the screen and it comes up. So that was my calculator problem all along. I could not figure it out because it seemed like it was starting up okay, but I couldn't see it anywhere. And the icon down here didn't pop up like this. It popped up with just like a black, a black little rectangle. So anyway, got the calculator figured out finally. 0.8925 minus 0.3632. And that gives me 0.5293. So about a 52.93 or about a 53% chance that our standard normal is between negative 0.35 and positive 1.24. And that was about in line with what we expected. Right. If this was as high as 60% or as low as 40%, I still wouldn't be suspicious. But again, if it was like 80 or 90%, or if it came back as 10 or 20%, then I would be pretty suspicious. I would want to take a look more carefully and see, well, was it my kind of gut feeling estimate that was off that I can correct? Or did I make a mistake somewhere in the algebra? Right. Maybe I got a little bit, excited or a little careless, and I just got my 0.8925 and said, okay, that's the answer, and typed that in, or wrote that down as the answer and forgot about the fact that I need to subtract off another probability or something like that, right? Or maybe in another context, I forgot to do 1 minus the answer. So getting a kind of ballpark estimate for your answer can be helpful for checking your answer, and also just for kind of building up an intuition for what's going on here. Are there any questions on standard normal distribution to this point, finding probabilities of events? Okay, so far we've been doing a type of problem that I kind of call a forward problem, where we are given an index and we're asked to find a probability or an area. But it's also quite important to be able to do what are sometimes called inverse problems. So oftentimes, there are kind of two natural, almost like mirror images. Oops. Almost like mirror images of a problem or of a mathematical scenario. And maybe one direction is kind of easy or more natural to do, and the other direction is more difficult to do. So, for instance, evaluating an expression, if you have, 3x plus 1, evaluating that at x equals 2 is a pretty easy process. But figuring out what input do you need to yield an output of, of 4 or something like that is maybe a more challenging process. So solving an equation is more difficult than evaluating an expression. Right. So evaluating an expression is kind of like a forward problem, and solving the equation is a little bit like an inverse problem. And that's what we have here. We have inverse problems that are kind of the reverse of what we were doing before. We're in some sense something like given area and asked to find the associated index. So we're given in some manner the number that's in the field of the table that's representing area or representing probability, and we're being asked to find an associated z index. So here my question is, I want to find a number k, so the probability z less than k is 0.05. So here is my standard normal distribution. Here's 1. Now I know that the area to the left of 0 is 50%, 0.50. I'm looking for a z index k with 5% area to the left. I know that k has to be less than 0. So that's a good check. I know that k has got to be negative, and it's got to be quite a bit negative to only have 5% area to the left of it. So my question is, what is the z index with 5% area to the left? I know it's going to be a negative index. It's going to be a negative z-score. Again, because if it was 0, if k was 0, it would have 50% area to the left. We'd be asking for probability z less than k equals 50%, 0.50. We're asking for 0.05. So I know it's got to be a negative index. I'm going to come through my table and I'm going to look for 0.5, or sorry, 0.05 in my table. So I see like 0.03, I see 0.07 that overshot a little bit. I see 0.516, 0.505, those are pretty close. 0.0495, 0.0485, those are pretty close as well. Now, typically when I'm looking for a z-index associated with probability, if I look in my table, in the field of my table, I'm typically not going to find exactly the probability that I'm interested in. So in this case, I realized that, okay, between these two numbers, that's where the 0.05 area lies. It lies between 0.0505 and 0.0495. So this answer lies between a z-index of negative 1.6 4 and 5. So negative 1.64, negative 1.65, something like that. Now, it turns out that this is a bit of a special case, this 5% area in one tail. And we actually have this little asterisk here denoting this special case. Figuring out an index with 5% area in one tail is actually a problem that comes up quite often. So the table actually gives us a little more accuracy in this case. If we follow the arrow down here from the asterisk, we actually see that a z-score of negative 1.645 gives us an area that's quite close to 0.05. So that was a special case for this particular example where we have 5% area in one tail. But for a more general case, we would just pick the area that is closest. In this case, 0.0505 and 0.0495 also, neither one of them is closer to 0.05 than the other one. Our answer here, 1.645, we really ought to use this for my stat lab. It's the more accurate answer, but kind of in reality, if you're using 1.6 or negative 1.64, negative 1.65, the difference between those or negative 1.645 is only in the third significant figure. And, that's usually not enough to make a big deal, to make a big difference in the end result. So I would recommend using the more accurate special case here in my stat lab. Note that there's also a special case for an area of 0.005. So 0.5% area in one tail. That's associated with an index of negative 2.575. Now, what if I and just a note, this is just the 5th percentile of the distribution, right? This is the outcome from Z that separates the bottom 5% of the distribution from the top 95%. It's just P5, or the 5th percentile. So we talked about percentiles back in chapter 3. This is the analogous idea in continuous distributions. And you can see there's really much less ambiguity about what a percentile means in a continuous distribution because we don't have this small number of data points to work with. There is a little bit of ambiguity in what percentile meant in chapter 3. Okay, what about this question? The probability of Z bigger than M equals 0.35. So I now have a right tail area of 0.35. I know that if M was 0, it would have 50% area to the right, and that's too much. So M has to be bigger than 0. So the area to the right is 0.35. Now my table doesn't tell me this right away, doesn't give me an answer right away, because my table gives me areas to the left. But here I could use symmetry, say. I could flip everything about 0. My curve looks the same. The M that was over here flips over to the left side as a negative M. And my right tail area of 0.35 becomes a left tail area of the same size, 0.35. So negative M is the 35th percentile. Or I come over to my table and I'm looking for an area of 35% of 0.35 in the middle here, in the field of my table. So I see down here I'm getting close. And between these two, between 0.3520 and 0.3483, that's where 0.3500 would lie. 0.3520 is 20 10,000ths away from 0.3500, and 0.3483 is 17 10,000ths away from 0.3500. So I will go with 0.3483 as a little bit closer. This 0.3483 area to the left is associated with a z-index of negative 0.39. So negative M equals negative 0.39, or M equals positive 0.39. For these right tail areas, so the left tail areas get, say, the 5% area to the left gets capital P subscript 5. It's like 5% gets a 5 in the subscript. These right tail areas are often called critical values or critical numbers. Critical values, I think, is more common. And they get a different notation. It would look like Z subscript 0.35. I don't know why they didn't make it Z subscript 35 to match with the P notation. So sorry about that. Two different notations. They do tend to be used in different contexts, but this is the notation for an area to the right of 35%. Be a little bit careful, because when your index falls between 0 and 1, it can look like a probability. 0.39 in different contexts could certainly be a probability. So be really careful to keep straight what's an index and what's a probability or an area. And especially when your index is between 0 and 1. It's really easy to get them backwards or get them confused. So be careful to keep straight which is which. We said that M should be bigger than 0, and it is. If we had, forgotten to switch the sign down here, we would have recognized from that check. All right, and then the third question down here. So here, I want the probability that Z ends up between two numbers to be 0.95. Now, I can't just say something like probability A less than Z less than B equals 0.95. What are A and B? Well, because I could have like A down here and B up here. Maybe this is 95% area. But if I shift A over a little bit, I can shift B over a little bit and maybe still maintain 95% area. So I could kind of shift the whole lowered upper bound left and right a little bit, and I would still be able to maintain 95% area. Now, if I shift A to the right too far, I don't have enough area overall to the right, even off to plus infinity, to have 95%. Or likewise, if I shift B to the left too far, but I could shift them back and forth at least a little bit and have multiple answers for different choices for A and B, where I have 95% area between them. There are too many degrees of freedom here to answer this uniquely. Roughly speaking, I have 2 degrees of freedom, two things to choose, A and B, and one constraint that the area between them has to be 0.95. And typically speaking, when I have more things that I'm able to choose than I have constraints imposed on the system, I'm not going to be able to find a unique solution. And that's the case here. What's different about the question that I asked here is we have an implied symmetry. In other words, I might phrase this in words as find the middle 95% of the distribution Z, of the standard normal distribution. So now, like if I pick this as a test N, then the symmetry implies that this would be negative N. If I move my N this way, my negative N moves that way and I get more area between. If I move my N closer to 0, my negative N also moves closer to 0 and I get less area in between. So as I start with N really close to 0, giving me 0 area between, and then I start moving my positive N to the right, my negative N moves to the left, and I increase area, I keep increasing. And at some point, I'm going to increase and be just below 95% and then hit it. And then from that point forward, I'm going to be past 95%. So I'm never going to come back down to 95%. I'm never going to have, you know, 2 N's or 3 N's or a bunch of N's that satisfy this constraint. And let me draw this a little more reasonably. I know that this is 1 and this is -1, and I've got 68% between those two. I know at 2 and -2, I've got about 95% between those. I expect N to be about 2 based on my empirical normal rule. I know the middle 95% of Z is about 2 because the probability that I'm within 2 standard deviations of the mean on a bell-shaped curve is about 95%. So let's write it a little bit on the inside of 2. It might be a little bit on the outside of 2. We'll see in a little bit here. Let me switch colors for this. Now we'll put -N here. So N might be a little less than 2 or a little bigger than 2. And I want this area to be 95%. Now, how can I find this area? Well, I guess I could think of finding this area if I was given, say, a particular N by taking the area to the left of N minus the area to the left of -N using complementary or something like complementary events, using the complementary events kind of idea. But I could also leverage symmetry here. I note that this has a lot of symmetry to this problem. I'm looking for the middle 95%. That's a symmetric area. Well, being a symmetric area tells me that this tail, the area over here, and this tail, the area to the right of positive N, they have to be the same size. So let's call this, I don't know, let's call it A, And then this would also be A. So what do I know? I know that 0.95, the green area, plus 2A equals 1. Or that basically tells me that the A's combined together give me what's left over after I take out that 95%, or they give me 5%. So A is 2.5%. So if I used up 95% of the area in the middle, that gives me a total of 5% for the tails combined between the two tails. But the two tails are symmetric because this is a symmetric region going from negative n to n and a symmetric distribution. So 2.5% area to the right of n and 2.5% area to the left of negative n. So I see it'll be a little easier to see that n is z subscript 0.025, or even easier still to see that negative n is the 2.5 percentile. Here I'm heavily leveraging the symmetry that's inherent in this problem. There's a saying in math that when there's a symmetry in a problem, if you choose a strategy that respects that symmetry, it usually pays off. So we're definitely trying that here, and I think it's paying off. Now, what is the 2.5 percentile of z? In other words, what's the z index that separates the bottom 2.5% from the top 97.5%? Well, I come over here and I'm looking for an area to the left of 0.025. And I see down here, I'm getting close. Here I've overshot a little bit. And here I'm right on. This actually turns out really nice. It turns out really close, 0.0250. We can't get more accurate than that in 4 decimal places. Now, this isn't exact. If we went out to 5 or 6 or 7 decimal places, it wouldn't just keep being zeros. But it's really close. It's definitely the closest on our table. So area to the left of 0.0250 is associated with a z index of negative 1.96. So I have that negative n equals negative 1.96, or n equals 1.96. And I indeed see that this is close to 2, as I expected. If it was a little above 2, I wouldn't be surprised at that, right? My picture would be slightly wrong if that was the case. I kind of made a guess that it was a little bit inside, a little bit below 2, that my area was a little bit inside of negative 2 to 2. But if it was a little bit outside, that would have been perfectly fine. I got an answer that's close to 2, which is what I was guessing. Any questions so far on this? Any questions on standard normal at all? All right, give me 1 second and I'll be right back. Okay, so jumping into general normal distributions now, or the normal distribution family. I think your book might call this something like applications of normal distribution, something along those lines. Okay, so let's look at an example here. We have a variable x that is normal, but not standard normal. Not normal with a mean of 1 and a standard deviation of 0, but normal with a different mean and standard deviation. Right? If we think all the way back to our formula for the normal up here, we had talked before about how changing mu and changing sigma affects the graph. Mu is our location parameter. If we change mu, it shifts the graph left and right. And sigma is our shape parameter. If we change sigma, if we increase sigma, it gets kind of flatter and shorter, or wider and shorter, wider and flatter. If we decrease sigma, decreasing the standard deviation, that pulls more of the area in close to the mean, our distribution gets skinnier and taller, gets more peaked. So the general normal distribution family is parameterized by mu and sigma. Mu can be any real number, sigma can be any positive real number. And these are, of course, the mean and standard deviation of the distribution, which is why we give these parameters these names. So here we're looking at an example of a normally distributed population with a mean of 100, standard deviation of 15. This might be a model for, say, IQs. This is kind of a fairly standard normal distribution example because IQ tests are actually normed, as they're called. They get the results in and they kind of make the cutoffs for different IQs, how many questions do you need to get right and what amount of time and all of that. They make those cutoffs, they choose those cutoffs to fit to a normal distribution, typically with a mean of 100, standard deviation of 15. Some of them have a slightly different standard deviation, and some of them have, just a different distribution overall, and you need some conversion to convert that to an IQ. But this is, I think, fairly typical for a lot of IQ tests. Mean of 100, standard deviation of 15, and follows a bell curve and normal distribution. So let's try to answer some questions about this member of this normal family. Kind of as an aside, we're typically going to be working with the normal distribution family, not with the standard normal, because you can imagine that there probably aren't a heck of a lot. I don't know where I wrote it down, but there probably aren't a heck of a lot of specific examples that have a mean of 0 and a standard deviation of 1, where that would be a good model. If we have more freedom to choose the mean and standard deviation to fit our scenario that we're dealing with, that makes this normal distribution much more useful. So something like IQs, where I want the mean to be 100, standard deviation of 15, I wouldn't use a standard normal for this because the mean and standard deviation are so far off of what I want them to be. This would be a much better model. Okay, so what is the probability x less than 100? Well, if I have a normal distribution with a mean of 100, I know my normal distribution is symmetric about its mean. Whether that mean is 0, like a standard normal, or whether that mean is 100, in this case, I still have symmetry about the mean. What's the probability x less than 100? What's the probability that we're to the left of this mean? Well, that's exactly half the distribution. That is exactly 50%. We can get that without even looking at the table. Okay, what about a more complicated question here? What about probability x is less than 115? So I want this area. Now I know the area to the left of 100 is 50%, and I have a bit more area here, so this has to be bigger than 50%. Now I have a little bit of an issue here. I do have a left tail area. It kind of matches this picture. But the issue is that the distribution I'm working with is a general normal distribution with a different mean and standard deviation than my z-score. These are only numbers related to the z distribution, right? These are for the standard normal distribution. If I wanted to have a table for even just say each integer combination of mu and sigma from from mu going from whatever, 0 to 100 and sigma going from, I don't know, 1 to 30 or something. I mean, I'd have a huge book of tables, and that wouldn't even, be all of my general normal tables. That doesn't seem like such a uh, good way to approach things. The magic of normal distributions is that any general normal distribution or any question in a general normal distribution can be rephrased or reframed as a question in a standard normal. If we come all the way up here, we've kind of ignored this function here for the time being, but let me actually bring this down, because I think if I hit enter up here, it's going to screw up all of the writing that I had. So let me bring this down here and do this discussion really quickly. So if I think about this, okay, well, this is just a constant. Let's just put k in there or something like that. That's just a constant. We can kind of ignore that. If I look at what's up in the power here, so I have an e to the power negative 1/2 times x minus mu squared over sigma squared, but that's just x minus mu over sigma all squared. Do we recognize x minus mu over sigma from anywhere? Say back in chapter 3, maybe. This was what we called the z-score. We didn't call it the z-score for an arbitrary reason. We called it the z-score because it relates to the standard normal distribution. But I noticed that if I chose mu equals 0 and sigma equals 1, up here, if I had chosen that originally, with these choices, what do I get? I get k e to the power negative 1/2. Well, mu is 0, so I get x minus 0 squared, or just x squared, over sigma is 1, so 1 squared is 1, x squared. Well, hey, those are exactly the same distribution. If I make a change of variables, z equals x minus mu over sigma, this converts back and forth between the standard normal and general normal distributions. Right, so if I took a general normal distribution with a choice, mu equals 0, sigma equals 1, this is the standard normal distribution. I see its PDF looks like some constant e to the minus 1/2 x squared. And if I did a change of variables for a general normal distribution with a mu and sigma that are not 0 and 1, and I chose z equals x minus mu over sigma, the z-score, I get a PDF that looks the same as a standard normal. I've just, with that change of variables, converted my general normal distribution into a standard normal. Let me erase a little bit of this up here. But this is really the key idea to the right. We can use the z-score, x minus mu over sigma, to convert back and forth between basically like general normal world and standard normal world. We can take a question that is phrased as a question of general normal distribution. What's probably this x, this general normal distribution is less than 115. We can use the z-score to reframe it as a question in z. And then, well, we know how to answer all the questions in z, whether they're forward problems or inverse problems. Right? We can use our table over here. We can use the tools and techniques that we had just discussed for many different examples in Z. So we're taking a new problem, we're doing something to reframe it as a previously solved problem, and then we're using our previous tools and techniques to bring the solution the rest of the way home. Okay, so if x is 115, then what's Z? Sorry, my allergies are just going haywire today. Between everybody trying to get their last grass cut in uh, for the fall and all of the leaf blowing and the leaves falling down and everything. It's all of the stuff that makes me allergic is like all over the place. So X is 115. What is the associated Z? Or another way of thinking about this is we're asking how many standard deviations above the mean is 115? When the mean is 100, standard deviation is 15. Well, remember, and for all of these, I'm just using the same distribution, mean of 100, standard deviation of 15. So 115 minus 100 over 15, that's 15 over 15 or 1. So I can rephrase this question, probability x less than 115, as probability z is less than 1. And what's probability z less than 1? Well, I can look this up off of my z table. I'll go to my positive z-scores. This picture looks like that one. I am looking for a left tail area related to a positive z-score, so that seems like we're on the right track here. And the area to the left of 1.00 is 84.13%. Now, one nice thing is that the areas, these probabilities are equal. The indices change, but the areas stay the same when I convert using the z-score. So this 84.13%, this answer that we got in the z world, is just as valid an answer in the x world. So I took my x index, I converted it to an equivalent z index, reframed the problem as a problem in the z world, the standard normal world. And once I did that, I said, oh, okay, I know how to solve problems that relate to standard normals. So I'll just go ahead and solve that. I get my answer, and that 84.13% is my answer. So what about probability x less than 123? Remember that inflection point is one standard deviation above the mean, or, oops, I wrote 0 there, 100, or 115. 123 is a little bit to the right of 115. So I'm looking for this area. I know this area should be bigger than 50%. It probably also should be bigger than 50% plus 34%. Should be bigger than 84%. That area between the mean and one standard deviation above the mean, that's 34%, half of that 68%, which would be the area within one standard deviation of the mean. And this is an index of 123, an X index. So if X is 123, then Z is what? X minus mean over standard deviation. 123 minus 100 over 15, or that is 23 over 15. About 1.53. We'll round to the hundredths place. That's the accuracy of our table. So 123 is 1.53 standard deviations above the mean. So reframing this question about x in terms of a question about z, we're asking what's the probability that z is less than 1.53. And here we can come over to our table. We're looking for a left tail area. The pictures do match. I'm looking for the area to the left of 1.53, or that's about 0.9370. That is bigger than 84%, which we'd expect. So it looks good. Any questions so far? Okay, what about this question? Probability x bigger than 110. So we have a right tail area now. So probably x bigger than 110. We're looking for the area to the right of 110. Now we need to do two things. Number one, we need to convert this to a question about z. And number two, we need to convert the right tail area to a left tail area. Kind of in theory, we could do them in either order. We could, if we wanted to, use the symmetry of the x normal distribution about its mean of 100 and convert this to a left tail area. What would that look like? We would flip about 100. Now, 115 is 15 above 100, so it would flip over down to here to 15 below 100 or 85. 110 is 10 above 100. It would flip over to 90, 10 below 100, and our right tail area would turn into a left tail area. So we could write this as probability x less than 90. I could do that. You can see, though, that that was pretty messy, right? I had to say 110 is how far above the mean. And then when I flip it over, I have to make it that far below the mean. It's pretty easy to make a mistake doing it this way. So in theory, we could do it this way. In practice, though, I think it's always best to get into the z world as quickly as possible. So we're going to convert the question into a question z with a right tail area. And z is super easy to flip over because its mean is 0. So all of the signs just switch, positive to negative, negative to positive, when I flip over to 0. It's a lot easier to flip over the mean of 0 in the z world than it is to flip over some arbitrary mean in the x world. So I'm going to switch to z as quickly as possible and then do all of my work in the z world. So our point of interest is x equals, oops, not 115, 110, this one here. And the associated z index would be 110 minus the mean of 100 divided by the standard deviation of 15. That is 10 over 15, 2/3, or about 0.67. I'm drawing this a little skinnier to get this graph and another on the screen. So here I have a right tail area in z. Probability x bigger than 110 is the same as probability z being bigger than 0.67. Now I need to do one more thing. I have a right tail area that I'm looking for in z. I need to switch it to a left tail area. I'll use symmetry to do that. You could use complementary events too, no big deal if you chose that approach. But if I flip about 0, that's much easier to do. My positive 0.67 becomes a negative 0.67. My right tail area becomes a left tail area. Again, I do recommend writing out all of the pictures because it really keeps everything straight. It's really easy to get an inequality sign wrong or a plus minus sign wrong if you're kind of just going through the algebra and trying to go that route. I think it's much more reliable to write the pictures out. And now this is a question we can answer directly from the table. It's not a positive z-square anymore because once we flipped it over, it's now negative 0.67 and the pictures don't match either. It is a negative z-score. We're on this side of our table. And I'm looking for the area to the left of negative 0.67. I have to scroll down here a little too far. It cuts off that top index row. But here's negative 0.6, that row. And the 0.07 column I can track down is this column. Or this is 25.14%. So about a 25% chance that a given person's IQ is bigger than 110. Does this make sense? Yeah. This whole area is 50%. The whole area to the right of 100. The area to the right of 115 is like about 15-ish%. So we're expecting an answer between 15% and 50%, and that's what we get. So it's in the ballpark that we're expecting. I guess I should have written 15 and 50 in blue to be consistent with my colors, but I think it's clear what I'm talking about. I'm trying to keep black and blue for the X world and green for the Z world. I'm trying to be kind of consistent about that. So the probabilities, the areas stay consistent from the X world to the Z world, but the index is what changes. So what's the probability X is bigger than 86? We're still working with the mean of 100 standard deviation of 15. We're using this same distribution for this whole example, for all of these little sub examples, just so we can kind of see what changes when we change problem type and not also be changing mean and standard deviation and all of that at the same time. So we can keep some things consistent and then see what changes as we change the type of question we're asking. So I know that one standard deviation away at 115 is that inflection point. One standard deviation below at 100 minus 15 or 85 is that inflection point. And 86 is just a touch to the right of that. And again, I want to rephrase this in Z before I go flipping or doing any of that. It's going to be much easier to do any kind of manipulation in the Z world where we have a mean of 0 than in the X world where we have a mean of 100. So I get that Z is negative 14/15 or about negative 0.93. Again, I have something that, I mean, it's negative, but you know, it at a glance might look a little bit like a probability. I want to remember this is a Z index, negative 0.93. Hopefully we would see the negative and realize pretty quickly it's not a probability, but this negative 0.93 is a a location on the z-axis, on the horizontal axis. So here's my inflection point at -1. Negative 0.93 is just to the right of -1. I'm looking for an area to the right in the x world, so I'm looking for an area to the right in the z world as well. So I could rephrase this as probability z is bigger than negative 0.93. As an aside, I know this should be bigger than 50%, right? Because it has all the area to the right of 100 in the x world, plus some more. And it should probably be close to about 85-ish percent. So close to something like 85%. That 50% plus that extra kind of -1 to 1, -1 to 0 standard deviations below the mean, which is about 34%. This is phrased as a question in Z, but it's an area to the right. Well, we just use symmetry, flip this around. My negative 0.93 becomes a positive 0.93. My area to the right becomes an area to the left. And I see this as the probability Z is less than positive 0.93. So the inequality sign changed and the plus minus sign changed. I'm looking for an area to the left on Z. I can use my table. This is the area to the left of a positive Z score. So I'm looking at the other side of the table. The picture doesn't match either. This picture matches a lot better. I do have a positive Z score, 0.93. So here's my 0.90, 1, 2, 3. So probability Z less than 0.93 is about 0.8238. That is bigger than 50% as we expected, and it's more or less 85%, which is kind of in the ballpark we expected. So that is my answer in both the Z world and in the X world. And what about this third problem type, where we have an event that's between two numbers? So we looked at an event where the variable is to the left of a number, at a couple events where the variable is to the right of a number, and this third kind of interesting event where the variable is between two numbers. What's the probability that X, a randomly chosen IQ, is between 85 and 115? And 85 and 115 happen to be both exactly 15 units away, or one standard deviation away from the mean, right at these inflection points. And again, before I really do anything, I want to convert to Z. I now have two X indices that I need to convert to Z. I need to convert each of these separately. So when X is 85, Z is 85 minus 100 over 15, or -1. And when X is 115, Z is 115 minus 100 over 15, or +1. All right, so my standard normal my area between 85 and 115 in the X world converts over to the area between -1 and +1 in the Z world. And here I guess I can use maybe a cheat. Then I know that this area is, say, about 68%. If I wanted to find it more accurately, I could use the table, but here I know that um, the probability of being within one standard deviation of the mean is about 68%. And this was work we had done last time, right? So we solved this last time. Let's look at a similar problem that doesn't line up so nicely with the z-scores of -1 and +1, though. So what about probability x between 95 and 105? So 100 in the middle. These inflection points where I change from going from curving up to curving down or vice versa are 15 points away from 100, one standard deviation away at 85 and 115. And 95 is pretty close to 100, and 105 is also pretty close to 100, just on the other side. 95 and 105. I'm looking for this area. This should be kind of a small area because it's kind of a small interval width. It's a small horizontal width. But it also occurs in the kind of chunkiest part of the distribution, right? Where a small accumulation of probability across a small interval can actually lead to a fairly large probability. So I don't think this should be like a really small answer, like 1%, but it also certainly shouldn't be, I mean, it doesn't take up this whole interval, so it should be definitely less than 68%. And probably a lot less, right? From our empirical normal rule, the probability you're within one standard deviation of the mean is about 68%. And we've cut out quite a bit of that area that's within one standard deviation of the mean. So we should be quite a bit less than 68%. I wanted that to be a double less than, so quite a bit less than 68%, but probably not something tiny like 1 or 2%. I wouldn't expect that. Because this is, a third of the interval width between 85 and 115, right? That's an interval width of 30, and we're thinking of an interval width of 10 here. So it should be a decent sized area, but not huge. And again, our X indices of interest are 95 and 105. So when X is 95, what is Z? X minus the mean over the standard deviation, or -5/15, -1/3, -0.33 rounded to 2 decimal places. And for X equals 105, same idea. Plus 0.33 rounded to 2 decimal places. Let me rephrase this question in X as a question Z. Again, could I have done my work over here in the X world to kind of build up this area as like the area to the left of 105 minus the area to the left of 95? Sure, I guess I could have. It probably would have been less difficult to do that than do the symmetry in the problem a couple of problems ago. But I like getting into the Z world as quickly as possible because we're more used to solving problems over there. So we have our question in X, probability X is between 95 and 105. That's probability Z is between negative 0.33 and positive 0.33. And this question in Z, I can rewrite as the difference of two areas to the left. So the area to the left of positive 0.33, that includes the area that we want to keep, that's between negative 0.33 and positive 0.33. But that also includes a bunch of area we don't want to keep. Let's get rid of that by subtracting off. So this is going to be the probability that Z is less than 0.33 minus the probability that Z is less than negative 0.33. And just kind of separate these two so they're not running into one another. And I can come over my table, probably Z less than 0.33, this kind of first picture on the right here with the red marks on it. That's a left tail area associated with a positive Z-score. The picture looks like the picture, so looks good. We will look for 0.33, and that gives me an area of 0.6293. So an index of positive 0.33 gives me an area to the left of 0.6293. And then for my negative Z-score, well, for my negative Z-score, the area to the left of negative 0.33. If I look at my rightmost picture over here that I drew, that meshes with this picture. It's an area to the left with a negative Z-score. So here's negative 0.30, 1, 2, 3. Negative 0.33 for the index should be associated with an area of 0.3707. And what does that turn out to be? 0.6293 minus 0.3707, or 25.86%. So like we expected, it should be quite a bit less than 68%, but not a tiny probability like 1 or 2%. This does meet those criteria, so it seems in line with what we expected. So I'm confident this is the answer. Any questions so far? Okay, so what if I want to do an inverse problem? The problems I've looked at so far in X have been kind of like forward problems, right? Where I have indices and I want to find an area. I could ask inverse problems in the X world as well. I could be given an area, say, for instance, a percentile, and asked to find an index. So X98, the 98th percentile, should be pretty far over here to the right of 100. We're looking for the X index that gives area to the left of 0.98. Now, something I realize here is that converting the X world to the Z world, that's a conversion of indices the probabilities and areas kind of we maintain those by carefully changing our indices using the z-score. But I don't know how to change x98 into a z-score because I don't have x98 yet. That's what I'm looking for. But let's kind of go with it. Let's say if we wanted to convert this picture into a z-score, we'd have some z-index. I don't know really what it is yet, but it would be related to x98. And the area to the left of that z-index would be 0.98, or this would be 98% area to the left of this z-score. But wait, that is just the 98th percentile of z. That's just P98. Well, I know that I can find P98. I know how to solve that problem. And then I need to write it in terms of x98. So what do we have? We have that x98 minus the mean over the standard deviation equals the z-score, P98. If I have my x-index and want to find the z-index like I had up here, I'd use it in this direction, plug the x in, simplify this fraction, get the z-score. If I have P98, or if I have the z-score that I've looked up off a table and I want to find x, I would say that x98 equals, well, I multiply by sigma, I add mu, P98 tells me how many standard deviations above the mean x98 ought to be. This is just a rewriting of the z-score. Mean plus z standard deviations. Mean plus P98 standard deviations. I know how to find P98. P98 is the z-score. It's the z-index with 98% area to the left. I know that's going to be a positive z-index, so not on this table, but on the other one. And I'm looking for an area to the left of 0.98. I'm looking in the field here for something that's as close as I can get to 0.9800. I see I'm getting close down here. And I think it's going to be right between those two, between 0.9798 and 0.9803. That's where 0.9800 will lie. 9798 is 2/10,000ths away. 9803 is 3/10,000ths away. I'll pick this one because it's just a tad closer. And I see this is associated with a z-index of 2.05. Well, so P98 is 2.05. The 98th percentile of z distribution is a z-index of 2.05. So here I almost started in the z world, and now I need to bring my information back to the x world, to x98. So x98, the thing that we ultimately want to find, the 98th percentile of the x distribution, is going to be the mean of x, 100, plus 2.05 standard deviations times 15, or just over 130. So 130.75. So an IQ of 130.75 would be at the 98th percentile of this distribution. Any questions on any of this so far? Okay, let's do one more of these, or well, two more of these examples. Let's do one more like this one, and then one that's an inverse problem with slightly different type. So what's x25, the 25th percentile of x? So again, I have our question in x. I'll still start in my x world, even though I might see that, I really could jump the gun a little bit and start in z and then convert to x. But I like to get my question written down in the x world so I get a good intuition about it. As kind of a side note, I think I forgot to mention up here that x98 pretty clearly should be bigger than 100. And we do note that it is bigger than 100. We might even say that it's bigger than 115 with pretty good confidence, and we see that that's true. So what about x25, the 25th percentile? The x index with 25% of the area to the left. Well, if x25, hypothetically, if it was 100, it would have 50% area to the left. That would be way too much. I know that x25 is going to be less than 100. It's going to be to the left of 100. It's going to have 25% area to the left of it. If I convert this to z, I'm looking for a z index with 25% area to the left. Well, that's just the 25th percentile of z. That is just p25. I know how to find p25. I can look it up on my table. And then I remember that my z-score is z equals x minus mu over sigma, or p25 is x25 minus mu over sigma. That is an equal sign on a minus next to that, but that's equals. I can multiply through by sigma, add mu, and I see that x25 is going to be mu plus p25 sigma. So p25, the z index, is telling me how many standard deviations I need to go above the mean. And if p25 is negative, I'll end up going some standard deviations below the mean. So what's p25? It's the z index with 25% area to the left. It's going to be a negative z index. So I know I'm on the other table. This also meshes better with the picture that I have over here. And I'm looking in the middle of the table, in the field of the table, for about 0.25. If I come down here, I'm getting pretty close. And between these two, between 0.2514 and 0.2483, that's where my answer lies. 0.2514 is 14 ten-thousandths away. 0.2483 is 17 ten-thousandths away. I'm going to go with 0.2514. It's a little bit closer. And I see that's associated with a z index of negative 0.6 and 0.07. So p25 is negative 0.67. That's the 25th percentile of my z my z distribution, my standard normal distribution. And that's going to plug in here. I can convert that over this direction to answer my question in x, the 25th percentile of x. The mean of x is 100 plus negative 0.67 times 15. or that is 100 minus 0.67 times 15, or that's 89.95. So an IQ of 89.95, or just about 90, would be at the 25th percentile of the distribution. Any questions so far? Okay, and then one last problem in the last 5 minutes we have here. The top 10% of IQs are at or above what number? So what's the cutoff for the top 10% of IQs? So again, I have my X distribution, mean of 100. The top 10%, I'm looking for the X index that separates the top 10% from the bottom 90%. That's going to be on the right over here. And it's going to have 10% area to the right. So I noticed that having 10% area to the right is basically the same as having 90% area to the left. This is just going to be X90. But we could also switch this over to a Z distribution. 10% area to the right is going to be 90% area to the left, or P90. We can find the 90th percentile of Z. We know that that's going to be a positive Z score, not a negative one. The area to the left of this Z index has to be 90%. That's got to be a positive Z score. So I'm looking in the field here for 0.9000, or as close as I can get. And let's see, I'm getting kind of close around here. And it looks like that's where my answer lies, between 0.8997 and 0.9015. 8997 is only 3 10,000ths off, and 9015 is 15 10,000ths off. We'll go with 0.8997. It's a bit closer. And that gives me a Z index of 1.28. My associated X index then, using my same rearrangement from up here, X90 is mu plus P90 sigma, or X90 is 100 plus 1.28 times 15. Or 119.2. So the top 10% of IQs are at or above 119.2. Any questions on anything we talked about today? All right, so next time we'll do one kind of final example here. We'll be looking at a different general normal distribution, so different mean and standard deviation, switch it up a little bit, and we'll work through a problem related to that.